Going to the playground. Tahi and Rua, it's interesting, 1 and 2. Tahi is sitting on the merry-go-round that is spinning clockwise. He is about 3 meters from the center and has a constant speed of 1.5 meters per second. So there's Tahi, 3 meters from the center, and I want to draw labeled arrows on the diagram to show the direction of Tahi's velocity and acceleration. I always spot where there's 2 things to do, because so many students only do 1 when there's 2 to do. So velocity is going this way, and I know velocity will always be at a tangent to the circle, so I labelled that one. And acceleration, and I should remember with circular motion that the acceleration always points towards the center of the circle. Okay, so I'm expecting that to be achieved because it's just some things that really I should remember. Calculate the size of his acceleration. Now this is circular motion, so if I remember from circular motion, I can look up at my formulae right way up at the top here, and I'm looking for my circular motion formulae. A equals v squared over r, so I need to now let's go all the way back down here. A equals v squared over r, and in my information at the beginning there, it told me the velocity was 1.5. Need to remember square that. It told me that the radius, distance from the center, was 3 meters. So let's put those numbers into my calculator. 1.5, and I need to square that. Divided by 3 equals 0.75 meters per second squared. Straightforward calculation, I hope. The mark will give me an achieved for that. State the direction of the horizontal force acting on Tahi, and I've got to explain why there must be a horizontal force even though his speed is constant. Okay, so I've got to remember this about forces and motion. Okay, so I remember that in circular motion the force is to the center of the circle. Fancy word for that, if you remember, was centripetal force. Why must it be there? The velocity is changing. This is the key thing. Because the direction is changing. Even though speed is constant. Okay, so we've got to remember that bit with circular motion, that the velocity is changing because the direction is changing. Change in velocity is an acceleration. An acceleration requires a force. Bam! Nailed it. So that there tells me quite a bit of information. I've given the direction, I've explained why the velocity must be changing, and I've explained why changing velocity should require a force. So I think that one should be an excellence question if everything in there is right. Commonly people miss bits out on there, and I would only get an achieved in that. Okay, let's have a look at part D. This one looks a bit complicated. There's lots going on here, isn't there? He climbs to the top of a slide. The slide is 4 meters high. I've got to do something about gravitational potential energy into kinetic energy. So there's going to be an energy thing in here. At the bottom he collides. Collides is always code for momentum. So there's going to be something to do with energy in here, and there's going to be something with momentum. The collision is inelastic. So I'm probably going to need to know something about what inelastic means. And Pi has a mass of 55, Rua has a mass of 65. Quite a lot of bits of information in there, and already I can see there's going to be lots to think about. What have I got to do? Don't forget, I've got to calculate their combined speed if they stick together after the collision. So I've got to show how I calculate Tahi's velocity. I've got to state what is meant by an inelastic collision, and I've got to explain two conservation principles. Whew, there's a lot in there. I think this is going to be a bit of a long answer. Okay, so let me think about what I'm going to have to do here. So I'm going to take Tahi at the top, gravitational potential energy, and I'm going to assume that's all changed to kinetic energy at the bottom. And I'm going to use that to work out what the speed is at the bottom. Oh, that should be not Ruas, that should be Tahi EK at the bottom, shouldn't it? And then they collide, so I'm going to use PF equals PI, momentum conservation, to find out how fast they're actually going after they've collided to get a final velocity at the bottom there. Gosh, there's a lot of work in there, and I bet this is going to be an excellence question. And if we scroll down here, we'll be ready to start with putting our answer together.